As time continues, high-performance computing faces ever-increasing volumes of data. Error-bounded lossy compression is a potential solution to this problem, enabling scientists to reduce the volume of data used by applications. My name is Robert Underwood. I'm a PhD candidate at Clemson University's School of Computing. My research interests are in lossy compression, reliability and fault tolerance, and high-performance computing. Exascale is driving high-performance computing to need to be able to process ever-increasing volumes of data. As you can see from the CESLE experiment and the HACK experiment, a large climate code and a large cosmology code respectively, as well as the LCLS2, a large X-ray instrument, the volumes and rate at which data is developing is increasing far faster than the recent systems that we've developed to process them. Compression can be the solution to this problem. Compression fundamentally represents data in a more compact fashion than it was provided by the user. There are two major kinds of compression: lossless and lossy compression. When you think of lossless compression, think of zip files. They have relatively high ease of use and data integrity because they preserve the data exactly as it was prior to the compression. However, this leaves many application scientists wanting because it doesn't achieve high compression ratios in floating point codes commonly used in scientific computing. This has led some to consider lossy compression. Lossy compression has high compression ratios, but suffers from a lack of ease of use because it no longer preserves the data integrity. Error-bounded lossy compression offers a middle ground. Like lossy compression, it has high compression ratios. And like lossless compression, it provides an error bound on the absolute value of the error that could be introduced, meaning that it has relatively high data integrity. What remains an open question is how easy is it to use. My dissertation argues that error-bounded lossy compression as it stands today is not approachable. There are too many interfaces, it's too difficult to understand, and too difficult to configure. My dissertation remedies these problems by providing a single interface to use, configure, and understand compression. For the remainder of this talk, I'm going to begin with an introduction to compression principles, overviewing the major techniques used in error-bounded lossy compression. After that, I will present LibPressio, the generic abstraction that I developed to unify the interfaces used in error-bounded and other compression methods. After that, I'll talk about the automated configuration of compressors through a series of papers that I've written, and then conclude with a discussion of understanding the effects of compression in future work. Let's begin with discussing the principles used in compression techniques. Here I have two pictures of Lake Hartwell, a beautiful lake near the university which I attend. The left picture is losslessly compressed. Notice the fine gradations of color and the smooth textures that we can see. The picture on the right is lossily compressed. Notice how there are artifacts and rough edges where the colors kind of bleed in together. However, the image on the right is 17 times smaller. Error-bounded lossy compression seeks to set a middle ground between these two images. The first method we'll talk about is SZ. SZ is a prediction-based compressor, meaning that it tries to use relationships between neighboring points in the data, either through a so-called Lorenzo predictor or a so-called regression predictor, in order to find commonalities between the data. After it's found these commonalities, it performs something called linear quantization, which rounds the floating point values to nearest scaled integer values, and then goes through two stages of lossless encoding. When we are unable to compress using the regression predictors within our error tolerance, we rather bypass the lossy layers and simply preserve that region of the data using the lossless compressors. ZFP is a transform-based compressor. By partitioning the data into blocks, converting those floating point blocks to fixed point by block, and then performing a near orthogonal transform. What the near orthogonal transform does is it, instead of representing the actual value at each position, it represents the value at each position as a sum of patterns. And by summing these patterns, you're able to more accurately condense the set bits within a given block to the upper leftmost side. From there, bit manipulation can be performed, followed by truncation, to achieve a desired precision. IMGARD is the third major air-bounded lossy compressor. It works by determining multi-grid coefficients. These multi-grid coefficients basically represent solving a coarser version of the problem at progressively and smaller subgrids. After these multi-grid coefficients are determined, the values are quantized and then losslessly encoded. At this point, we can note that none of the compressors that we've talked about so far, whether lossless or lossy, share the same interface. LibPressio exists to be a generic abstraction for the compression of dense tensors. LibPressio provides common abstractions for everything that you need to commonly perform compression tasks: loading compressors, configuring them, compressing and decompressing data, representing data, reporting errors, configuring metrics on that data. And as you can see, it's relatively simple to use. The code on the right represents everything that you need in order to run a compressor. And the sections highlighted in boxes in red represent the things that you have to change if you wanted to adapt to a different compressor. To this end, LibPressio already supports a wide array of compressors, metacompressors, metrics, I/O modules, and tools used by a variety of different organizations. So what exactly is a metacompressor? Metacompressors exist to boost productivity of developers using compressors. They are not compressors themselves, but provide common services used in compression, things like auto-configuration tools, pre- or post-processors, and parallel runtimes. LibPressio also solves problems for its users. Writing for multiple compressors is difficult. In the process of developing LibPressio, we found over 100 various bugs that lay users might encounter when using new compressors for the first time. Now, what about using this in a more real-world application? Let's look at the case of zchecker. So I did a study looking at how many lines of code could be saved by using LibPressio exclusively to replace the code within zchecker for handling compressors. What I found is that by using LibPressio, zchecker could save over 1,000 lines of code, 20% of the code used to interface with compressors. And while doing so, it would gain access to 10 new compressors, 3 additional data formats, and they would be able to better take advantage of parallelism through MPI, and is supporting new compressors with just a recompilation. So where do we want to take LibPressio in the future? I want to look at supporting sharing of accelerators such as GPUs, threads on a CPU, FPGAs, as well as better support for asynchrony in streams and support for sparse problems. Now let's talk about the automated configuration of compressors. We'll do so through a set of 3 papers, beginning with FRaZ, Fixed Ratio Compression, published in IPDPS 2020. The question we aim to answer with FRaZ is, can we tune compression using a control loop to bound the compression ratio? To begin, we're going to formulate the compressor configuration problem as an optimization problem. We will let Q be a function which returns the compression ratio. From there, we'll allow the vector C to be the error bound in the compressor. Then we'll let the set U represent the set of allowed error bounds for the compressor, and DFT represent a data buffer for a particular field and time step. From there, we have a compression function, d tilde-ft, which returns the buffer after it has been decompressed. Finally, we'll let theta c be the error-bound mode if the compressor has one. The first thing we might ask is, why not just solve this problem with some bisection technique like binary search? And the short answer is that it doesn't work. The relationship between the error bounds of a compressor and the compression ratio that it can achieve are not always monotonic, as you can see from the figure on the right. This non-monotonicity enfeebles techniques like binary search. Now we must ask, what can we use? So we turn to the domain of numerical optimization. Within numerical optimization, there are analytic-based methods, which solve for the derivative using calculus, numerical-based derivatives, which estimate the derivatives by looking at successive points, and derivative-free based methods that don't use the derivative at all. What we found is that the analytic-based methods that use the derivative are too challenging to use. This is for a couple of reasons. One, the compressors frequently change, meaning that any work that you use to base off an analytic derivative is likely to change with the next release of the compressor. Additionally, It's often hard to mathematically describe the relationship between the air bound of a compressor and the derivative that it has to achieve. Next, we turn our attention to numerical-based derivatives, and we largely found that these were too slow for the purpose. Evaluating the compressors, the only way we have to relate an air bound to a particular compression ratio, can take several seconds. This makes it too slow for practical use. This leaves us with derivative-free base methods. Specifically, we chose a method based off dlib's find global min, with some optimizations that we talk about in our paper. The first question you might ask is how much overhead does a method like this take? And what we found is that the overhead is only 2 times what an oracle would take in the feasible case. If you look at the figure on the right, you can see that all of the feasible air bounds, that would be the air bounds of say 9 and 10, and then 21 and onward, are feasible air bounds with very low overhead relative to the time it takes to perform the compression. The remaining air bounds happen to be infeasible. This is largely due, in the case of the underlying compressor, to the lossless encoding stage. What we found is that low compression ratios in the range of 2 to 6 just simply weren't possible due to the amount of data that we would inherently get by using the lossless compressors. Additionally, there are regions in the search space of targets that also aren't achievable, like for example in 13 to 17, for similar reasons. So how do we get to this level of performance? We do so by using 3 levels of parallelism. First, parallelizing by field, and we do this through an embarrassingly parallel algorithm. Second, parallelizing by time step. We do this by recognizing that typically in scientific simulations, the data is relatively smooth in time, meaning that we can reuse configurations found for prior time steps as a good estimate for the next time step. When we did this in our work, we found that for a typical 40 to 50 time step simulation, we only had to retune on the order of 5 to 7 times over the course of the entire search. Finally, we parallelize by air-bound range. Essentially what we do is we split up the search domain into several slightly overlapping chunks. The reason for the overlap is to ensure that there are sufficient stationary points for the optimization algorithm to find a solution in the regions in which there is an overlap. When we find a solution, we terminate our search early. Let's move on to the second work, LibPressio-Opt, which attempts to bound user metrics and includes performance improvements, currently in submission. The question we ask here is, can we extend FRaZ to bound simple user metrics and improve performance? We'll begin with the same formulation we used in the FRaZ paper and make several modifications. First, we'll introduce a new parameter, theta m, which represents the fixed metric parameters. From there, we will redefine Q from being the compression ratio to now being the user airbound metrics function. Next, we will redefine the airbound as the non-fixed compressor settings. These are the settings that we will allow to vary over the course of our optimization. When making this changes U from being the set of allowable airbounds to the set of feasible compressor settings. From here, we redefine theta C from the airbound mode to the compressor fixed parameters. These are the parameters that we will allow not to vary over the course of the optimization. The notation being redefined, let's look at a quick illustration of the relationship between the various notations. Notice that C is a member of U, which is a subset of omega, the set of all configuration parameters for a particular compressor. Notice that theta C also represents an element of omega. It is important to note that theta m is drawn from a different parameter space. We also notice the uncompressed data buffers D and the decompressed data buffers D' represent separate sets. In this understanding, the function d tilde ft c of theta c is a mapping from D to D'. With this understanding, we can talk about the concept of constraints on the objective. If we have a function, let's say, wanting to achieve the greatest compression ratio subject to some image quality metrics, such as the PSNR, the peak signal to noise ratio, or the SSIM, the structural similarity index measure, we can construct a function q of I and with the threshold tau of I, which represent bounding these particular metrics. With this, we can construct a piecewise function, q, which we can then optimize upon if we wish to constrain the objective. At this point, I'd like to be a little more rigorous in defining what I mean by a metric. For the purposes of LibPressio-Opt, metrics need to be sufficiently deterministic, have a fixed number of real valued inputs and outputs, and can be modeled as having a single objective. So let's take these one by one. What do I mean by sufficiently deterministic? A metric is sufficiently deterministic if the variation induced by non-determinism is relatively small relative to the degree of indeterminism caused by the change of the parameters of the metric or the underlying data. Having a fixed number of real valued inputs and outputs means that as long as we can represent them as some sort of operation on fixed-sized vectors, we can use the metric. Finally, it's important that it can be modeled as having a single objective. For the purposes of LibPressio-Opt, we typically represent this by the first element of the vector. Now let us consider a collection of types of metrics. The outermost type we will consider are real-time metrics. These are metrics that can only be computed at runtime. They cannot be computed from the buffers after the fact. A good example of this would be compression time. Obviously, you don't know how long it took to compress and decompress a buffer simply by looking at the values of the buffers themselves. Next, we would have application metrics. Application metrics are things that are application specific. That means that they have a specific number of buffers that they need as input and output, and they cannot be computed on any possible collection of buffers. A good example of this would be a accuracy measure from a machine learning code, or maybe a spectrum from a cosmology code. We're not going to focus here. The next class of metrics that we will consider are multi-buffered metrics. These are metrics that could be computed with any number of buffers. A good example of this would be compression ratio, because you could simply sum up the sizes of all of the uncompressed buffers and divide them by the size of all of the compressed buffers to compute a compression ratio from any set of buffers. Finally, we will consider single buffer metrics. These are metrics that can be computed from any pair of individual buffers. A good example of this would be the image quality metrics, PSNR, or the peak signal to noise ratio, or SSIM, the structural image similarity metric. We will focus our study on these last two categories because, one, they tend to be more deterministic, and two, don't put specific requirements on how the application metric is structured. Now let us consider a competing technique in the same space. IMGARD has a mode that they call quantity of interest mode. With the quantity of interest mode, they place some additional restrictions on the metric that they are considering. First, they require that the metric under consideration be a bounded linear functional. Essentially, this means that for this particular object, the distributive property holds. Additionally, IMGARD for the quantity of interest mode requires that the input buffer be a regular grid. To be fair to IMGARD, this includes a wide array of simulations commonly used in high-performance computing. So how does this work? Fundamentally, they compute a scaling factor which is used to adjust the norm used and preserved by IMGARD. The process for doing this is quite mathematically intensive, and the details can be found in the paper below. Now, once they've computed this scaling factor, they simply multiply the norm, which is currently and normally preserved by IMGARD, by this scaling factor in order to determine what value to preserve in their particular problem. So how do we perform relative to IMGARD's quantity of interest mode? What we found is that by using LibPressio-Opt in conjunction for FRaZ, we found that we can actually vastly outpace what IMGARD's quantity of interest mode is able to achieve, especially on one-off tasks. The way that ImGuard is constructed, it's actually able to reuse the scaling factors for all problems that have similar enough physics. So if the physics problem is substantially similar enough, you only have to perform the pre-computation once. So if your problem definition is rapidly evolving, LibPressio-Opt is going to be substantially faster than whatever you can achieve using ImGuard's quantity of interest mode. However, even if pre-computation is not required, LibPressio-Opt using SC can still potentially be faster. This is because the underlying compressor used, in this case SC, is substantially faster than the current implementations of ImGuard. We can further say that ImGuard's quantity of interest mode tends to over-preserve the amount of information. This means that the resulting compression is less compressible than what LibPressio-Opt is able to achieve. Finally, it is actually possible to use LibPressio-Opt in conjunction with ImGuard. By using these techniques together, you can maintain the particular mathematical guarantees offered by the ImGuard compressor while achieving higher performance than what is possible for rapidly evolving problems. What about comparing our techniques to what we did in our prior work, FRaZ? Relative to FRaZ, LibPressio-Opt has a faster early termination system called inter-iteration early termination. Essentially, it allows for the search process to be terminated in between individual iterations in the parallel search process. Additionally, LibPressio-Opt allows for multi-threaded searches for compressors that support it, such as EFP. It features an embeddable interface rather than an application interface, meaning that it can be used within the scope of other applications since it doesn't have its own main function. It supports user-defined objectives that can potentially consist of multiple different constraints on the objective, such as those that might be used by the climate community. Finally, LibPressio-Opt allows for searching over multiple different input parameters and allows you to extend the search methods. We hope to use these techniques in the future to inspire our future work looking at more complex applications. The question we aim to ask here is, can LibPressio-Opt be used to bound complex, multifaceted user metrics, such as those used in the Harbor Hybrid Accelerated Cosmology Code, or HAC for short, specifically the power spectrum that's used within that application? For those unaware, HAC is an ECP astrophysics particle application. It simulates the state of the early universe. One of the metrics that the users are interested in HAC is the power spectra. An example of this visualized is seen on the right. What is important to note is that no currently existing compressor bounds something as sophisticated as this visualization. So how could we approach this problem? We could approach this by implementing the power spectra as a LibPressio metric of type vector of double. In doing so, we then can compare these two vectors in order to have some idea of how different the respective power spectra are. There are currently several different metrics that are known to be useful in comparing spectra when viewed in this way, such as the Cieto distance or the log spectral error. By using these metrics and potentially others, we hope to solve for the maximum compression ratio such that the differences between the spectra are acceptable. I will close out with some future work in this area. The first of which is true multi-objective compression. This means that we want to look at multiple different factors simultaneously and use all of them to guide the compression, rather than just treating the objective as one black box value. Next, we want to improve the search algorithm. While the search algorithm that we have has allowed us to achieve high degrees of performance, we think there's more performance that's possible to be taken off the table. Specifically, the current search algorithm leaves a large amount of time being very eager in searching new regions in order to guarantee high performance. However, a technique that looks more at refining existing areas may be more performant. Lastly, we'd like to look at better task scheduling techniques to further reduce the runtime involved with scheduling the various tasks. Now I will briefly touch on the impacts of being able to understand the effects of compression by a case study in machine learning and AI applications. The question we aim to answer in this area are what are the trade-offs for compressing training and testing data to save storage space against the quality metrics used in various machine learning and AI applications. We will approach this in 3 stages. First, we will apply varying degrees of compression to various training and testing sets used for machine learning and AI. After that, we're going to compute the quality metrics that the individual applications are most interested in. This could be things like precision, recall, so on and so forth. When we do this, we will not develop models ourselves, but rather reuse so-called best-of-breed implementations of the various problems, trying to be as realistic or close to realistic as possible. Finally, we'll evaluate trade-offs between the various points by looking at them as a Pareto curve to identify points that are optimal. To do all of this, we will use LibPressio and specifically its so-called external metrics functionality to enable to run scripts to collect the data points that we care about. The figure on the right represents an example of some of our findings. When we compared against a wide variety of different compression techniques, we found that compression based off of prediction in air-bounded lossy compression, such as SC, tended to work best. We found that it worked even better than the sampling techniques and was more consistent, even on problems where the balance of the dataset was not very good. Additionally, we found that in some cases, air-bounded lossy compression actually improved performance. So why did this happen? Fundamentally, we think this happens because the machine learning or AI application was essentially over-learning aspects of the individual data. And the error introduced by the air-bounded compressor essentially smoothed off some of this over-learning that occurred. So what way of organizing the data tended to work best? What we found is that for tabular data commonly used in machine learning and AI, it was best to compress that data using a relative airbound mode by feature. This means that we are able to achieve the tightest airbounds on the individual features, preserving them as accurately as possible. In conclusion, air-bounded lossy compression has the potential to be transformative, especially when scientists are equipped with an interface to unify, tools to configure, and tools to understand the results of air-bounded lossy compression. I hope you found this talk interesting. At this point, I'd like to take a brief moment to thank the various scientists at various institutions that have helped me over the course of my dissertation, as well as the organizations that have funded me over the course of my research. If you have any questions about this work, feel free to reach out to me at my email, robertu@g.clemson.edu. If you follow the QR code here, you can also find my curriculum vitae. Here are the papers that make up my dissertation, as well as the papers that I referenced over the course of this presentation. Finally, I will acknowledge funding by a variety of different organizations that have funded various aspects of the research that I've presented here today. Thank you all.